Section 2.1 is about definition of a vector space. So here is the definition. Let me mention right now that there will be simpler alternative, but we do have to go through the rigorous definition. A set V is called a vector space over the field F if it has, first of all, a binary operation plus such that this set V with the addition is an abelian group. Of course, this abelian group has a lot of properties that come with it. I don't want to spend much time defining what an abelian group is. I mentioned even the field. We're not going to go through all the possibilities in general. So let me mention right now from abelian group what we have is, first of all, it's not empty. Of course, that's very important because for empty sets there are too many properties that are satisfied. In general, in mathematics, it's very important to avoid dealing with empty sets. Sometimes it might turn out that you have a very nice set with very nice properties, but if it turns out that it's empty, then it's really not interesting. Another important property is that it's commutative and associative, and that it has the identity element. With respect to the addition. So this is denoted by 0 in general, and the property of the identity is that for all vector in this vector space, if you add to the vector this 0 vector, that's not going to change the vector. So you get back the vector itself. Let me also mention that this addition, this binary operation, can be said to be a mapping from V cross V into V. So what it does is that if you have V and W vectors in this vector space, then when you add them together, this will be also a vector in the vector space. Property B of a vector space is that it has a scalar multiplication in addition to the addition. So the scalar multiplication goes from the field cross V into V, and the way it works is that for all A element of the field and for all vector of the vector space, we have that A times V is also a vector in the vector space. This is the definition of the scalar multiplication, or the notation for it. The property of this scalar multiplication, several properties. First one, for all scalar in this field and for all u, v vectors of the vector space, we have that A times u plus v is the same as A times u plus A times v, which means that this is distributive. Scalar multiplication is distributive. With respect to vector addition. We can distribute the scalar A to the parentheses term by term. Second property, for all AB scalars and for all u vector from the vector space, we have that A plus B times u is the same as A times u plus B times u, which means that we have the distributive property also with respect to the scalar addition. Another property, for all v vector from the vector space, 1 times v equals to v is in the vector space, where the 1 is from the field F, is the identity element, which means that the definition of 1 is that 1 times A is A for all A in the field. So this might be confusing. What's the deal that 1 times a vector is just a vector by itself? It has to be listed as a separate property because we are defining the vector space, and 1 is a scalar, and the only property that originally we defined for 1 in the field is that 1 times A is A for elements of the field. Now the vectors are completely different, so it's kind of a unique property that this also holds when instead of A you replace this field element with vector v, and still it holds that when you multiply it with 1 you get back the original vector v. Property 4, for all AB elements of the field and for all u vector element of the vector space, what we have is A times bu equals AB times u. And it's important that what we have is that when you multiply the u vector with b, you get a new vector. You can scalar multiply it with A. And this identity says that instead of that, to scalar multiplication, we could just multiply u with the product of AB, which is another scalar. This is called the associative property of scalar multiplication. First example, we will use this a lot. R2, which is so-called Euclidean vector space. that will be the vector space V. So the way we can also write this down is that it's two vectors. Sometimes I will use column vectors, sometimes I will use column vectors, sometimes row vectors. It doesn't matter. So it has usually two coordinates, x1 and x2, and x1, x2 are real numbers. And we consider this as a vector space over the field F, which is also just a set of real numbers. As I mentioned before, in this class mostly we will consider fields that are either the real numbers or complex numbers. We're not going to consider abstract fields. All right, so how is it a vector space? We have to define okay, so you might say that, oh, again, this is trivial, something you saw even in high school maybe, but let me remind you that this is a definition, the way we define vector spaces. So we define scalar multiplication, for example, we have A from the field, which is again just real numbers, and then the vectors, we have these two vectors. I might write with indices v1, v2, the two components, and then the scalar multiplication will be defined as component-wise multiplication. So AV1, that's a real number because you are multiplying real numbers. AV2, another real number. And then by the definition of the vector space, this is again in the vector space. And then of course we also have to define addition, not just the scalar multiplication. So if you have two vectors like V with components v1, v2, and U with components u1, u2, all these are from the vector space, then we define V plus U, the sum of these two vectors, we add them component by component, and again both components are real numbers, so we have another two vector. We can easily check that if we consider 1 from the field, which is again just a real number, we have 1 times V is multiplied component by component, 1 times V1, 1 times V2. But because these are scalar numbers, we have that this is just V1 and V2, since 1 is the identity of the scalars. We also have the 0 vector as the 0, 0 vector with both components 0. We can also check that this has the property that if you add together any vector with this 0 vector, you get the original vector back. Let me write down that f equals the complex numbers, set of complex numbers, is another frequently used field. So the next example for vector spaces, after this very simple example with R2, will be prototype example with functions. Again, this will be now very abstract, so we go back and forth between very abstract and simpler vector spaces to try to demonstrate and get used to working with vector spaces. S will be any non-empty set. Okay, so this is also important maybe to remember, that any non-empty set. F will be any field in general. And then we let the vector space to be, the notation is f raised to the power s. And the definition of this is that this is the set of functions mapping from S to the scalar field F. We have to use functional notations. First we define the addition. How do we add together functions? For all fg from this vector space, f plus g is supposed to be a function mapping from S to F, and we have to define then this new function. So the way we define function is that we write down the formula for all S from this set S. We have to define what the value of the function is. So f plus g is a function, and the obvious way to define it is that we add together the values f of s and g of s. And since these are already in F and we have addition in F, we see that this is in F. We also have to define scalar multiplication, which will be similar to the addition, for all A in F and for all F in V. AF is a function mapping from S to F, defined as for all S from the set S, the value of AF at S is that you scalar multiply the value of f of s. And this is actually now the multiplication from the field. So the multiplication in the field is supposed to be already defined. That means that this should be in the field. So this was an example for a vector space, and this is a very abstract example. Let's see a specific example, specific case of this. A simple set S could be just two numbers, 1 and 2. For the field F, we set it to be the real numbers as usual. So then, as a vector in the vector space V, F is supposed to be function from S to F. That means we have functions from the set 1, 2 into the real numbers. So the domain is the set 1, 2 basically, and then we are mapping into R. One possible notation could be that for the F, we write this, we have to have the values at 1 and 2, and we can just collect it together into a vector. So once we know what the value of the function f at 1 and 2, we know what the function is. That's how we define a function, through its values. Okay, so we can just say that this is how the vector space is built up. And what you see here is that then if you have these two components, this really looks like just R2 with two components. And then this set S with the two numbers, these are really could be considered just the indices like x1, x2 for two vectors. Another example, another case of these function vector spaces, instead of just two values, so let me remind you that the sets are denoted by braces. Now if we set S, the set S to be with the bracket notation 0, 1, this just means the interval between the closed interval 0, 1. Another way to write this, we will use set theoretical notation a lot here. So this is the set of all x's that are real numbers such that the vertical line denotes the such that notation, such that x is between 0 and 1 with equality allowed at 0 and at 1. So this is the set S. Then let's consider again F to be the set, the field to be the set of real numbers. Then according to the definition we had before, this F to the S that we had here, these are the F functions from mapping from the 0, 1 interval into the real numbers, right? So we cannot use now the previous vector notation because instead of two entries x1 and x2, we have infinitely many over the interval 0, 1, infinitely many elements. Yeah, so S could be any set in the general definition. Before we used S equals to 1, 2, the set of two numbers. So this is a typo, it should be indices. So before we had just two numbers in the set S. Now we have infinitely many elements in the closed interval 0, 1. So this is definitely more interesting than what we had before. If you try to show some vectors in this set, so we have the 0, 1 interval, and then we're supposed to have some kind of functions. So this could be one function, yeah, this could be another function, like g. Actually, we didn't even specify that this function should be continuous or what kind of functions they could be. So maybe we could have even step functions or piecewise defined function, f, g, h. So f is an element of V, g and h are also elements of V. And you see the pictures of them, just functions. The addition would be defined like regular function addition. So the way we define the sum of two functions is that you evaluate the sum by adding together the values of the individual functions. F plus g is a new function, and its value at x is f of x plus g of x for all x 0, 1, and for all f, g from the vector space. That's how we define addition. Scalar multiplication is also simple. So you scalar multiply a function, you get a new function, and the value of this new function at x is just 8 times f of x. The 8 times the value of f at x. Again, for all a from the field, which was the set of real numbers, for all f vector which is really a function, and for all x from the 0, 1 interval. Another popular example, often used vector space. So the problem with this previous vector space, or one potential problem, is that I didn't specify what kind of function I'm talking about. It could be piecewise defined, continuous, or differentiable function. And then it could be very esoteric function. So some special function that people often use in applications is denoted by p sub n, and this will be the polynomials in x from a field f, which is typically the real numbers, with coefficients. Polynomials have coefficients. Again, in f, which is usually the real numbers. The polynomial should have degree less than or equal to n. All right, so for example, we have p3. Another way to write this down instead of with words, well, degree 3 or less polynomials. So that should be with coefficients real numbers. And the variable is x. So it's ax cubed plus bx squared plus cx plus d. This is the most general way to write down a degree 3 polynomial. And of course, if a is 0, then the degree is less than 3, like 2. If b is 0, then it's just 1, and so on. So here what we have is that a, b, c, d, the coefficients are from R, and the variable x is also from R, real numbers. So n should be some kind of positive or zero integer. Actually, we have to talk about what p0 is. Well, maybe let's go back to first p1, from p3 to p1. So degree 1 at cx plus d, cd are from real numbers. X is a real variable. And then, so then this still has x to the 1, the first power. Then if you want to go back to p0, degree 0 polynomial, so this is really just a constant functions. So if you think about what 0 polynomial has, we're supposed to have an identity. Let me denote it with lowercase p0 of x. So this is just the identically 0. This is supposed to be in each of the polynomial vector spaces. And the way we can make this consistent is that we set its degree to minus infinity. And then what we have is that with this p0 of x is in all Pn vector space. How do we add together polynomials? Well, it's supposed to be the same way as we did before for functions, and in how we did it even in elementary school. So if you have, for example, v vector, that's really now a function 5x cubed plus 4x squared minus 2, for example. That's in P3. And if you have another vector, w, it's a quadratic polynomial, x squared plus 6, but it's also actually in P3, since in P3 the leading coefficient a might be actually 0. Then if you have two vectors, then the way we add them together is just simply adding together like terms, 5x cubed plus 5x squared plus 4. And then, of course, this is also in P3. Yeah, so we have the plus operation going from P3 to P3, P3 cross P3 to P3. Then the scalar multiplication, for example, minus 2 times W. So minus 2 is a scalar, in our case, a real number. W is this vector, which is really a polynomial. Well, we just multiply term by term, as we would do in an algebra course. And of course, you see that this is also in P3 then. If you multiply this vector with the 0 scalar, then we get this P0 function of x, which is the identically 0. And then this is also in P3, since its degree is considered to be minus infinity, and minus infinity is less than or equal to 3.